Hi everyone, we now learn about the binomial distribution. In particular, we're going to be learning about the binomial probability distribution function, which we'll often simply call the binomial PDF. Now to learn about this, we're going to work through the example that we see here, in which we're told that a biased die is such that the probability of rolling a 6 is p, which equals to 0.4. We're then told that the die is rolled 8 times, and we're asked to find the probability of 1. Getting exactly 3 sixes, 2. Getting exactly 6 sixes, and 3. Getting at least 1 6. Now, as I work through this example, I'm going to use the upper left-hand corner here to help you understand how to recognize that this can be modeled by a binomial distribution, and to remind you of, or introduce you to, the binomial probability distribution function. Finally, I should say, if ever you're not interested in seeing any further explanation, and all you want to see is me work through the example you have here, then I've added timestamps or chapters to this video that you can access through this video's timeline. So don't hesitate to skip from one section to the next. Either way, let's get started. Looking at the example we have here, we can definitely model this with a binomial distribution. And in fact, I'll make a little bullet point list here. I'll just say binomial distribution. So in a binomial distribution, we're dealing with an experiment which has two outcomes. Experiment with two outcomes. Those being success or failure. And so looking back at our example here, each time we roll a die, a success would be getting a 6, and a failure would be not getting a 6. So I'll just write that. A success would be getting a 6, and a failure would be not getting a 6. And of course, each of these two outcomes has its own probability. The probability of a success here is given in the question. Indeed, the probability of rolling a 6 is p, which equals to 0.4. So I can write that here. The probability of a success is 0.4. And the probability of a failure, which I'll call q, will therefore be equal to 1 minus p, which in this case would be 1 minus 0.4, which is 0.6. The next bullet point I write for the binomial distribution is that this experiment is repeated n times. So I'll just write experiment repeated n times. And in the case of this example, we're told that the die is rolled 8 times. So here, n is equal to 8. Finally, the last bullet point I make here is to indicate that each trial, so each time we repeat the experiment, is independent from the previous. So I'll just write is independent. Okay, now for this particular example, what this last bullet point is telling us is that whatever I get on any one roll of the die won't affect what I get on the next roll, which seems quite safe to assume. Okay, now provided these three criteria are met, we can use the binomial probability distribution function, or binomial PDF, to calculate probabilities like the ones we're being asked to find here. But before doing so, we need to define a discrete random variable, which we typically call capital X, and is defined as the number of successes in n trials. So number of successes in n trials. So that's n trials of the experiment. So for this example, the discrete random variable capital X would be defined as the number of sixes we get, so I'll just write number of sixes, in 8 trials. And so hopefully it's clear. If we roll this die 8 times, then the number of sixes we could get would be either 0, 1, 2, 3, 4, and so on, all the way up to 8 sixes. And each of those possible outcomes has a probability. And that probability can be calculated with the following formula. The probability that x be equal to r is equal to the binomial coefficient nr times the probability of a success raised to the power of r times the probability of a failure raised to the power of n minus r. And I'll go ahead and box that. This is known as the binomial probability distribution function, or simply binomial PDF. And I should say this binomial coefficient nr could also be written as ncr, and in fact quite a few textbooks write it that way. And don't worry, they are both calculated in the same way and both refer to the same quantity. What this is saying is that the probability that the number of successes be equal to r is equal to the binomial coefficient n, r, times the probability of a success raised to the power of r, times the probability of a failure raised to the power of n minus r. And so just to make sure that I've written down what r represents, I'll write that underneath here as r is equal to the number of successes. Number of successes. Okay, so this is the function or formula that we're going to be using. Now let's work through this example to see exactly how we're going to use it. And so I'll start with question 1. We need to find the probability of getting exactly 3 6s. In other words, we need to find the probability that the number of successes equals to 3. Remember, x was defined as the number of 6s we get in 8 trials. Now, copying the right-hand side of this formula with n equals to 8, r equals to 3, and replacing p and q by their respective values, 0.4 and 0.6, the probability of the number of successes, or 6s we get, being equal to 3 is equal to the binomial coefficient 8, 3, times the probability of a success, so that's 0.4, raised to the power of 3, times the probability of a failure, so that's 0.6, raised to the power of 8 minus 3. And that's equal to the binomial coefficient 8, 3, times 0.4 raised to the power of 3 times 0.6 raised to the power of 5. All we have to do now is calculate. And don't worry, our calculator actually has the binomial PDF function built into it. But for the sake of this first question, let me remind you of how you would actually calculate this binomial coefficient 8, 3. And I'll do that up here. The binomial coefficient 8, 3 is equal to factorial 8 over factorial of 8 minus 3, so that's factorial 5, times factorial 3. That's equal to 8 times 7 times 6 times factorial 5 over factorial 5 times factorial 3. We notice here that the factorial 5s at the top and the bottom cancel each other out. And we also notice that since factorial of 3 equals to 6, it cancels out with the 6 at the top. And so we're left with the binomial coefficient 8, 3 equals to 8 times 7, which equals to 56. And so we could replace this binomial coefficient 8, 3 by 56. Finally, and by all means check, but plugging all of that inside my calculator, I find that that's equal to 0.279, where I've rounded to 3 significant figures. Done. Now, calculating all of this the way we just did can be rather tedious. And luckily for us, our calculators have the binomial PDF function built into them. And the only information we need to feed our calculators for it to calculate all of this in one go is the number of trials, so 8, the probability of a success, so in this case 0.4, and the number of successes we're interested in, so in this case 3. In other words, I could have said right away that this equals to binompdf, PDF, with inputs 8, 0.4, and 3. And my calculator would have given me this result directly. And I should say, my calculator is a Texas Instruments calculator. If ever you have a Casio calculator, then it's not called binompdf. The function you're looking for is called binomialpd. And the order in which you would enter these 3 values is slightly different. Indeed, on a Casio calculator, you need to enter binomial, PD, and the first thing you enter is the number of successes you're interested in, so in this case 3. You then enter the number of trials, so in this case 8, followed by the probability of a success, so in this case 0.4. And provided you enter that correctly, you'll get this answer. Okay, now that we've seen how to write the calculation in detail, and we've mentioned which function to look for on our calculator, let's quickly work through the questions 2 and 3. Question 2, we need to find the probability of getting exactly 6 6s. In other words, we need to find the probability that the number of successes equals to 6. Well, first of all, using the binomial PDF that we have here, we can state that that's equal to the binomial coefficient 8, 6 times the probability of a success, so 0.4 raised to the power of 6, times the probability of a failure, so 0.6 raised to the power of 8 minus 6. So that would be 2. And it's worth writing this because you're showing your teacher or the examiner that if you had to, you would know how to do this by hand. Once that's done though, we can go ahead and write that that's equal to binompdf, with 8 trials, a probability of a success of 0.4, and the number of successes we're interested in, 6. And by all means check, but with my calculator and rounding to 3 significant figures, I find that that's equal to 0.0413, and that's rounded to 3 significant figures. Done. So the probability of rolling 6 sixes in 8 trials is 0.0413. Alright, we move on to the third and final question, in which we're asked to find the probability of getting at least 1 6. In other words, we're being asked to find the probability that the number of successes, capital X, be greater than or equal to 1. Now, at a first glance, you may think this is a bit complicated. Indeed, the formula we have here gives us the probability of X being equal to a specific value. Here, on the other hand, we need to find the probability that X be greater than or equal to some value. And there are quite a few outcomes that correspond to X being greater than or equal to 1. Indeed, since we're rolling this die 8 times, then for X to be greater than or equal to 1, we could get either 1 6, 2 6s, 3 6s, 4 6s, and so on, all the way up to 8 6s. And in fact, I could write that this equals to the probability of getting 1 6, plus the probability of getting 2 6s, 3 6s, and so on and so forth, all the way up to the probability of getting 8 6s. But rather than doing all of this, we could use the fact that the complement of getting 1 6 or more, in other words, the complement of X being greater than or equal to 1, is X being less than 1, in other words, X being equal to 0. So we could go ahead and state that this is equal to 1 minus the probability that X be equal to 0. And that's equal to 1 minus the binomial coefficient 8, 0, times the probability of a success, so 0.4, raised to the power of 0, times the probability of a failure, so 0.6, raised to the power of 8 minus 0. So that's 8. And now the binomial coefficient 8, 0 is equal to 1. 0.4 raised to the power of 0 is also equal to 1. And so all we actually have to calculate is 1 minus 1 times 1 times 0.6 to the power of 8. And by all means check, but with my calculator and rounding to 3 significant figures, I find that that's equal to 0.983. And that's the answer. And so the probability of getting at least 1 6, in other words, the probability of getting at least 1 success, is 0.983. And there we go. That's it for this example. We now know which conditions or criteria need to be met in order to be able to speak of a binomial distribution, and we also know the binomial probability distribution function and have seen how to use it. And that's it for this tutorial.